Welcome. In this video, I'll show you how to solve problem 2.20 as it appears in both the second and third edition of the book. Now, this problem is quite long, and let's read it quickly. It says, this problem is designed to guide you through a proof of Plancherel's theorem by starting with the theory of ordinary Fourier series on a finite interval and allowing the interval to expand to infinity. So basically what we want to end up showing is something quite similar to this, except that in the limit where a goes to infinity, of course, which is what we use whenever we are, or in many problems, when we are dealing with the packets of waves moving freely through space, right? The free particle case, which is what we have been seeing before. So we have used it before, but proving the theorem itself is very important, and it also really reinforces some tricks, like Fourier's trick, that we're going to be using often, not only on this course, but also in others. So part A says Dirichlet's theorem says that any function, almost any, on the interval minus a plus a can be expanded as a Fourier series, right, like that. And we want to show that this expression can be written equivalently as a sum from minus infinity to infinity of some constant times ein, or rather coefficient, times that exponential. And we want to find what is Cn in terms of an and bn. So let's begin. How could we approach this? Now, what I would encourage you to do is that whenever we want to go from sines or cosines to exponentials, that should be a relatively strong sign that we may want to use Euler's formula. Now, this may not always be what you actually have to do, but if you're uncertain where to start, that is a pretty good try. So the sign of npx over a, we can rewrite as, let me do it like this, e to the I n pi x over a minus e to the minus I n pi x over a divided by 2i. And we can do the same for cosine, except that the formula is somewhat different. It is the sum of these, so e I n pi x over a, and then plus e to the minus I n pi x over a, and all of this divided by 2. Okay, so these two formulas are very important if you're unsure where they come from. They are both derived from the fact that ei theta is cosine theta plus I sine theta. You can write it as also in the negative form, so e to the minus I theta, which gives you cosine theta minus I sine theta. And from here you can add these two together or subtract them, and you can get each one of these formulas. Okay, so that's where it comes from. But basically solving for cosine or sine from these two equations. Okay, so now it is looking a little bit better because we have these exponentials, but we also have, basically we have e to the I n pi x over a, which is what we want, but we also have one that is negative. So let's put everything together that we do want and see what happens with the rest. So let's go n equals 0 to infinity of, now let's put here everything that is multiplied by e I n pi x over a. So that is going to be multiplying an divided by 2i plus bn divided by 2. And then we have another sum. This time, same limits, but this time it is e to the minus I n pi x divided by a. And that's going to be factored by, let's see, we have minus an this time over 2i plus bn over 2. Now, notice that these two expressions are almost the same thing, except that here we have minus n instead of n. So something that we could do is do a change of variables here and basically say, okay, let's allow n to go to minus n and change every n to minus n. And what is that going to do? That means that in this expression, we will now have plus n equal, and now because of this, the limits will basically be reversed. We're going to start off at minus infinity, and we are going to end at 0. Because before, when we went to infinity, we had the term e to the minus and very, very, very large n's, right? Basically minus infinity. And we started off at e to the 0. So now we have the exact same thing, except that our limits are reversed, but the sum is the same. It doesn't matter if it's in the first position or in another position. The sum is the same. And now the exponential will be e to the I n pi x over a, right? And you can check. If I put in n equals 2, for example, or in this case minus 2, which would be the third term, right? 0, 1, 2. We would get e to the minus 2I pi x over a, which is the same as if I had plugged in 2 right here. So it is the same. And now we have these coefficients. You could maybe rename n here to like minus n, but it refers to the same thing, okay? So as long as you are, you know what you mean, you can also keep this notation here. But the important thing is that now we transformed this sum into one that has a positive exponential. So now we can put both of these together into one single sum again and factor by this exponential. And we can define a constant Cn that has two possible values. It is an divided by 2i plus bn over 2 if n is greater than 0, right? Here where we are summing over positive numbers. And it is minus an over 2i plus bn over 2 if we are summing over negative n's, right? But what happens in the limit where n is equal to 0? Well, let's quickly check it out. So what happens if we take this formula, and so basically what is C0, right? So when n is 0, the exponentials, both of them are 1. So we are left with a0 over 2i plus b0 over 2. This is this part. Plus, or actually minus here, minus a0 over 2i plus b0 over 2. So C0 is simply B0. Okay? So this has the value B0 if n is equal to 0. So using this constant that is now defined piecewise, we can write our function f of x as simply the sum of n equals minus infinity to infinity of e to the I n pi x over a times this coefficient. And there we go. We put everything together. All we had to do was write out sine and cosine explicitly. We factored everything together. And then we just changed the limits here by changing the name of our variable n. And that was it. And then we had to, of course, define the coefficient that put everything together. So we managed to find this in terms of an and bn, as you saw. Okay, pretty cool. Now we want to do part B. It says show by an appropriate modification of Fourier's trick that the Cn that at the moment is inside of this sum can be written as the integral of minus a to a of the function f. Basically, we want to turn this around because the way that this works is that if you know Cn, you can find the function. But we want to do it the other way. If I have the function, can I find Cn? That's what I want to do now. So let's go for part B. Now, what we're going to do is, as I mentioned, as it was in the problem, it is a modification of Fourier's trick. And that is incredibly important trick to know. The trick says that it is basically, we want to get rid of the sum, right? So how do we get rid of this sum right here? Well, we can get rid of a sum if we add a delta, delta here, right? So for example, if we have delta of something, I'm not gonna spoil what it is just yet, but it includes n, let's say n to some other variable m. This is 0 if n is different from m, and is only not 0 and has value 1 if n and m are equal. So for that reason, it doesn't allow n to run over the entirety of the values that it normally can, but rather it only lets it exist when n is equal to m. Okay? So that is why we want to introduce it, because it kills the sum. Okay? And that's how we can free Cn from the sum. Okay? So how do we free the coefficient from inside of the sum? We need to find a way to create a delta function. And how do we do that? With Fourier's trick. So what is Fourier's trick? Well, Fourier's trick, and again, if you have never seen this, don't worry. I mean, it's a very difficult trick to think of. But you have to learn it if you don't come up with it yourself. So what we do is that we integrate within the region that we're interested in. So from now, minus a to a. And we are going to integrate e to the im. Very important, a different one that is here. And we're going to make it negative. So e to the minus im pi x over a dx. So we're going to integrate both sides by this. So we multiply by this exponential and we integrate. So let's go. We get left-hand side minus a to a e to the minus im pi x over a f of x dx. And on the right-hand side, we have the sum still. The coefficients, they don't depend on x or on m, so they can stay outside of the integral. There's nothing going on there. But now this the exponential does depend on x, so that does have to be considered inside. So we get e to the I n minus m times pi x over a dx. So now the trick here, or what we have to do, we already used the trick, but the difficulty, or rather what we have to do, is solve this integral. So let's call it integral I and go here to the right-hand side. So I, notice that this includes this n minus m, but both n and m can be any two integers. So what do we do here, right? M is simply an integer. I don't know if I said it before, but it is just like n, any integer. Right, so I'm just going to write it m integer. And n is also any integer, and you're summing over minus infinity and infinity. Now m is just one integer, right? It doesn't change, but it could be anything. So you will always have one instance where n is equal to m. And every other instance, n will be different from m. So there are two cases, right? Because we're going over every single number, every single integer number. So you cannot avoid n and m being equal at some point. So let's go for n equals m first. So case 1. So if they are equal, then n minus m is 0, and you're simply integrating minus a to a of dx. So this is 2a. Nothing too crazy. That was pretty easy. Now, case 2. When n is different from m. So in this case, we actually have to solve this integral. But that isn't really a difficult one to solve. It is simply an exponential. So the exponential will be itself after we integrate. But we have to divide by these things. So I n minus m over a times pi. And we have to evaluate this between minus a and a. So we get these constants here. So that is a over I n minus m times pi. And then we have e to the I n minus m times pi. Notice that x and a cancel out. And then we have minus e to the, let's see, I minus now n minus m pi. Why minus? Because we plugged in minus a for x. Okay. Now notice that we have now e to the I something minus e to the minus I something. And we have an I outside. So there's actually several different ways to do it. I would do it like this. I would just put the I in here, multiply and divide by 2, so that we're not doing anything illegal. And notice that this is simply the sign of n minus m times pi. What you can also do, something that is also valid, is that you can take these exponentials and write them out using Euler's formula, right? As cosine I sine, both of them. With both of these methods, you will get to the same outcome. And the outcome is that this thing right here is sine of n minus m pi. And what is this? Both n and m are always integers. So it will be always sine of either pi or 2 pi or 3 pi or 4 pi or minus pi or minus 2 pi or minus 3 pi. So either way, this is always 0. So this thing is always 0. So if n is different from m, then the integral is always 0. So basically, the integral, right, I, this is 2a, sorry. So this is 2a if n is equal to m, and 0 if n is different from m. So basically, I is 2a times delta nm. And there is the delta function. That is why we multiply it by this integral, because it is a very clever integral, right? Because we look at what is inside, and Fourier knew that if you multiply these two exponentials together, you get this integral, which gives us this delta function, right? It is the definition of the delta function, basically. That is the trick. So we can now go back in here and plug this in here. So this entire thing, we already know, is simply 2a times the delta function nm. Okay, and the delta function, what does it do? It says the only allowed value where the delta is not 0 is when n is equal to m. So the entire right-hand side is a bunch of 0 plus 0 plus 0 plus 0 plus 0 plus 0 until we get to that one particular value, and that one still exists. So we get 2a cm. And then we have the integral here on the left-hand side. So minus a to a e to the minus I m pi x over a f of x dx. We can divide by 2a and write this a bit prettier, and we get 1 over 2a. This is equal to cn. And there we go. Well, cm. Even though it doesn't matter, you can, now that we are done, you can rename it and just call mn, right? You can say, okay, let's rename it, and it is now n, right? It doesn't matter. It is simply a name. You can call it n star mk, I don't know, do whatever you want. So there we go. We found this result. So now comes part C. Now, using the results that we found in A and B, we want to now eliminate n and cn in favor of the new variables k and f of k. And now why do we want to do that? Because now these new variables, because before we had just this case where we have only integers, right? It is a very discrete way of writing it. It is not continuous. So now slowly we want to begin using more continuous variables. So we're gonna define this variable that is not yet quite continuous, but will allow us to go there. So we are told to define the new variables. K is n pi over a, and f of k, which is square root of 2 over pi times a dn, right? So using that, we now want to see what happens with what we found in part A and part B. So what we found in part A is right here. So this thing right there. Now let me try to see both at the same time. There we go. So let's plug this in here. All right, so what is Cn? Well, Cn, simply from here, we see that it is square root of pi over 2, and we have to divide by a times f of k. So that was quite simple. Now let's plug it in. So doing that, we have that f of x, this thing right here, is now the sum of n from minus infinity to infinity of Cn, which is square root of pi over 2, 1 over a, f of k times e to the I n pi x over a. But notice that we also defined k as n pi over a. And that is exactly what we have right here, e I n pi a. So we can rewrite this as e to the I kx. And you can see that now, this is why we use that notation, because now it is looking like what we are familiar with, right? The traveling waves. Eikx we know is the traveling wave, the wave is traveling to the right. And now it is no longer a function of x, right? There is no x in here anymore. It is now a function of k. So this is f of k. Let's see, how are we doing? So there's now this final step, delta k, where delta k is the increment in k from one n to the next. So if we are here, if you go from one n to the next, so for example, if we have n equal 1, then k is pi a. But if we now go to n equals 2, then k will be 2 pi over a. So it changed by pi over a. So that means that the increment in k is pi over a. Okay? So that's what we want to add here. But where can we get the pi over a from? We have square root of pi here, so what we can do is multiply and divide by the square root of pi. That way we are not doing anything illegal, and this pi and this pi can combine, and they can form pi. So this will be 1, and this will be an entire pi. And we have a here, so this a that you see, we can combine it with this other pi, and we get pi over a, which is delta k. And now we can rewrite this a little bit cleaner. We can put everything in the square root together. So we can write this as 1 over the square root of 2 pi times all of this. And there we go. Now we included delta k, the interval. Okay, amazing, the increment. Now we want to do the same, but for the expression that we found for f of k, which is from part B. Let's see if I can. Is this it? Yeah, this is it. So this is what we now want to use. So now we do exactly the same thing, but here. So I'm gonna just call mn. Again, it doesn't really matter, but I like to use n more. Now, Cn, as we saw, is square root of 2 over pi. So actually here, we want to plug that in. So we get square root of pi over 2, 1 over a, f of k. And now this is equal to this entire thing. So 1 over 2a. What else? Integral from minus a to a, e to the minus, and again, n pi over a, well, that's simply k. Minus I, well, do we actually, wait, do we want to do that? Let's make sure. Actually, no, we don't want to do that. Why not? Because we are integrating in x. That's why I immediately hesitated. Yeah, we are integrating in x, so we don't actually want to plug it in just yet. So minus I n pi x over a, right? Yes, so over a. And actually, no, I'm lying. We do want to do that. And now n pi over a, that's simply k. So I k x f of x dx. So this part is easy. Simply solve for f of k. So here we get, well, the a's cancel out. So we get, let's see, 1 over 2 times square root of 2 over square root of pi. This cancels out a little bit, and we get 1 over square root of 2 pi, integral of minus a to a, e to the minus I kx f of x dx. And there we go. We now showed that this here is indeed true. So there we go. Then we have part D. It says take the limit where a goes to infinity to obtain Plancherel's theorem. And let's do that. So in this part, so D here, if now a goes to infinity, now what happens to k? If a goes to infinity, k becomes smaller and smaller and smaller. And for that same reason, delta k becomes smaller and smaller and smaller. So now delta k becomes simply a differential. It goes from delta k to dk. Okay? So that means, and the sum now will go, it will not really be a sum anymore because we're not summing over just these integers. We are now going over every possible value. So it's no longer a sum, it is now an integral from minus infinity to infinity of dk. There we go. So, and there we just found the first part. So pretty quick. And the second part is even quicker. This thing right here. If this goes to infinity, if a goes to infinity, then simply we change the limits. And there we go. Now we recovered Plancherel's theorem. And this is something that we will be using very, very often in this course whenever we're dealing with free particles. So yeah, that's pretty interesting. I hope this was useful to you. If it was, please do make sure to leave a like on the video, comment and subscribe. It doesn't cost you anything, but it really helps me out a lot. I'll see you in the next video. Thank you very much for watching.